I would propose to have this solution with batteries that run out after a certain fixed amount of energy. That it just totally doesn't make sense to me. Why would it would be so natural that we are generating the power locally at those sensors. And that picture in my head, it really gives a comfort that this is, from first principles, a very logical solution for powering IoT devices. This year, actually throwing away about 18 million batteries per day. And that is, of course, a shocking number because that means that we are generating a lot of waste with all those batteries. But also, we are spending a lot of manual labor essentially to replace all those batteries. If we are even replacing them at all, I know that in many cases, the batteries are not being replaced, but it's the whole sensor that is replaced. Which means that we are now not only having had this 80 million batteries as a waste, but also maybe 40 or 50 million sensors as well.
Hello, Raj. Thanks for joining us in Scouted by Graby. I'm really happy to see you here. And right away, I'd like to first ask you, is there anything exciting going on with Memsys that maybe public doesn't know, but you would like to share with me?
Yeah, thanks once again. Very happy to be here. And yeah, there are a lot of things happening right now behind the scenes. So we released about 3 months ago our latest prototype, which was the one from the first quarter of 2025. And we are right now making some really cool decisions on how the next prototype is going to look like and what that exactly is going to entail. I cannot say, of course, but we are trying to, again, push the boundaries of our energy harvesting prototype with more power in a smaller box, smaller volume, and a broader bandwidth. And that is super exciting.
It is exciting because when I read about Memsys, and actually how I found Memsys is basically we were doing some research on ambient IoT. We were trying to figure out what kind of interesting innovations is are going there. So a lot of companies which are working in this ambient IoT tech, they are focused a lot more on heat, using residual heat or using ambient lighting to power electronics and sensors. What struck me about Memsys was that you guys are using vibrations to power that. So, and again, even though I'd like to dive deeper into it, I'd like to know basically how this tech is working on that scale, because I saw the picture. The sensor is just like this small, right? Harvester, I think quartz harvester that you, if I'm getting the product name right. So can you tell me, like, how is this working? How are you able to utilize vibrations?
A lot of them are using vibration of a thermal and a light, and that is a relatively mature technology for both of them. Actually, solar panels have been around for a while, and these Peltier elements have been around for a while as well. Now, vibrations has been receiving a lot of interest from the research, but application-wise, it has remained quite difficult to get that to work in a real-world environment. And that is because vibrations continuously change. So you have maybe a machine that vibrates in a particular way with a particular frequency at one moment, and then something happens, maybe the speed changes or some other conditions change, and the vibration looks a little bit different, right? It has a little bit of a different frequency. And particularly that has been quite challenging for vibration energy harvesters to address. And that's exactly what we are doing. So we are creating some mechanical structures that have the ability to vibrate along with changing vibration environments. So we do that through a mechanism called a compliant mechanism. So that is a monolithic structure that gets its motion from deformation. Instead of having like hinges and joints where the mechanism can move, such as you're used to in most of the mechanisms around us, this type of mechanism is moving because it is internally deforming. And we combine that with piezoelectric materials that once deformed, they generate a little bit of power, a little bit of electrical potential that you can capture, then you can store that and you can use it to power a sensor. So how our systems how our systems work is through these compliant, flexible mechanisms combined with piezoelectric elements.
Thanks for sharing this. And actually, you already answered my next question, because that is also something I was curious about. That because piezoelectric sensors have been there, but I'm aware of the challenges. They need a consistent type of vibration, a specific type. Only then they are able to like work at full efficiency. And I read that Memsys has already figured out a solution for this. That your sensors can work with inconsistent vibrations, and basically they are able to provide consistent power. So do these inconsistent vibration, they affect the power output of Memsys harvesters?
Yeah, they for sure do. So if your vibration is not completely stationary, so completely the same frequency and amplitude, but it shifts around all the time, then of course your power that you generate at that moment is going to shift around as well. But the philosophy that we try to adopt is we want to make a system that can have a guaranteed power level for, of course, a certain level of vibration, such that we can assure that we at least are able to capture that amount of power if there is a vibration. And then if that vibration changes a bit, maybe in frequency, maybe in amplitude, the power, of course, it will fluctuate, but it will not have this massive, for example, a 99% drop that you typically see in some of the resonator type systems that are described in literature, which perform really well and have very impressive power numbers at a given type of vibration. And then when it changes, maybe even a few hertz, really, the frequency, the power just dramatically drops. And yeah, it's almost useless, the system. And so what we try to achieve is a system where we have let's say maybe a bit lower power level compared to some of those resonators, but at least we can sustain that even if the frequency changes, maybe even tens of hertz away from what you originally had.
Okay, that sounds like very. I mean, I think that is the core challenge, I guess, as you painted of current resonators. So it's good to hear that you have already figured it out. Thanks for sharing that. How Memsys system is managing varying vibration. So even if the power output is a little bit lower compared to current market available resonators, you are able to do it on consistent level, and power doesn't really dramatically drop even if the vibration changes. So that is very interesting to see. I'm also interested now because you mentioned that your numbers are impressive in term when it is compared to the current market available resonators, specifically in these varying conditions. So can you share some numbers with me? Is there any calculations done, any impact numbers you'd like to highlight?
Yeah, so our most recent prototype, which we revealed about 3 weeks ago, that is I would say, a 600 cc box, so 600 cubic centimeters, and that is fairly large for an energy harvester. And we make it quite large because it allows us to iterate really fast on the mechanism design and on fabrication. But that was able to achieve quite a wide range of vibrations over 1 milliwatt of power. And if you're used to, for example, how much power your PV panels on your roof produce, then 1 milliwatt does not sound like a lot. And frankly, it is a minuscule amount of energy. We are, of course, continuously improving that. We are also shrinking the volume that this mechanism occupies. We have a lot of room there to improve on that. But the key part was that we were able to demonstrate this 1 milliwatt of power over a range of almost 40 hertz of varying vibrations. And that is then not 40 hertz, let's say 1040 to 1080, but it was 40 hertz around a 50 hertz vibration. Anywhere between 30 and 80 hertz, roughly, we were able to capture at least 1 milliwatt of. And that could easily translate into a real world application where you have maybe a pump or a motor somewhere in a factory running at a inconvenient to reach location. And even if that motor or pump is a variable speed, still we could guarantee that enough energy can be harvested such that we can power a wireless IoT system.
I was impressed until you said that the 40 hertz vibration was in a 50 hertz system. Then I was like really impressed. This is amazing to see that in a 50 hertz system we are able to generate enough power. And I agree, 1 milliampere, I think it was 1 milliampere power. I'm sorry, I totally skipped.
Yeah, well, about 1 milliwatt. So that's
1
typically we
milliwatt height.
characterize them in microwatts because if you calculate the
Even 1 microwatt, I agree, sounds very small.
yes, yeah, it
Sorry.
is. It's a minuscule amount of
So
energy, right?
yeah, but I agree. I think all piezoelectric sensors currently in the market, they work in similar ranges. They are not like solar panels generating in like kilowatts of power. So it makes sense. And of course, I think as long as we are talking about industrial IoT, I guess sensors are so small that they will be able to utilize this power very easily. So it makes perfect sense. And now that I
Absolutely.
think this,
With
yes,
this
yes,
with this
yes.
1 microwatt of with this 1 milliwatt, to put it in perspective, what that could mean already for some sensor applications that we're looking at now is we can transmit and measure quantities like vibrations 6 times more often than they can currently do with their battery powered sensor. So it's the same sensor, but swapping the battery that then of course has a lifetime attached to it that makes sense on an industrial scale. So for example, like 3 or 4 years, calculating back what power that would allow you to use on a per second basis. So how much energy per second you can use with that finite power budget of the battery. Then calculating that back to a power figure, then we see that we are now 6 times ahead of what is currently being used. So that means measuring and sending 6 times more often because you're now using an energy harvesting technology instead of a battery.
Makes sense. I think this is what makes sense, right? In industrial setting, there could be like thousands of sensors that are required to monitor and analyze the situations, and it doesn't make sense to have all of them battery operated and then managing the power and then replacing the batteries. A lot of environmental waste will be generated. So I see a clear benefit of this tech. But I'm sure you might have some numbers, or you might have done some testing on your end to showcase that environmental impact, or basically how easy it will make life of industrial operators who are dealing with like thousands of IoT sensors, if they have some way to utilize this vibrational energy to power their sensors. So have we done any kind of testing like that for Memsys?
There are a lot of reports on this, and I'm sure you're familiar as well with them, that we are in this year actually throwing away about 80 million batteries per day. And that is, of course, a shocking number because that means that we are generating a lot of waste with all those batteries. But also, we are spending a lot of manual labor essentially to replace all those batteries, if we are even replacing them at all. I know that in many cases, the batteries are not being replaced, but it's the whole sensor that is replaced, which means that we are now not only having had this 80 million batteries as a waste, but also maybe 40 or 50 million sensors as well, and all of the components that go into that. Many of the sensors in industrial settings are completely encased in epoxy, for example, and cannot even have their battery replaced without throwing away the whole device. And that is exactly what we want to fight by developing this energy harvesting technology and the applications for it, that we can make a bit of a dent in that 80 million battery plus maybe 40 million sensors that we are throwing away every day in IoT.
I think you're bang on right. A lot of sensor, they are so tiny that they don't have external batteries they have their batteries embedded. So on industrial scale, it doesn't make sense in terms of even labor cost to replace each and every battery. So it's easier to throw the whole sensor away than to replace the battery. And I also believe that's a huge problem that needs to be solved. So, and I'm very happy to see that there are like some startups working on this and even finding creative solutions to this. I think using vibration is like a creative solution to that. I'm also curious about the applications of your sensors. Like where can they create a direct impact, or which are the industries you're targeting initially, where you can showcase how easy it is to implement your Memsys technology? And does it require a special mechanism to be introduced in a value chain of a factory, or is it like is it a plug and play system? So can you take me through that?
Yeah. So we are currently pursuing a strategy where we are looking for partners in the sense of sensor manufacturers, because we don't intend to go build out all the sensor applications ourselves. So we want to focus on the energy harvesting technology and delivering that as a power source for these wireless sensors. And there are too many sensor applications for too many different customer segments to be focusing on all of them at the same time. So what we see in terms of how the technical development looks like is that it's of course easier for us to make a bit bigger system and test mostly those dynamic properties, this wide bandwidth and the power generation at varying frequencies. That's a bit easier to test at a bigger scale. So first point on that roadmap are some external systems where we essentially have a power supply box that contains then the energy harvester and some buffer, electrical buffer capacitors, or even small rechargeable batteries in there. And we hook that up to a existing sensor. So that value proposition there, it allows the sensor user to get a lot more performance out of that same sensor without worrying about the lifetime of the battery, for example. That is the first types of products that we envision. And those are, you should typically think at predictive maintenance use cases. The second step there, I think, are much smaller internal power supplies that can be placed in IoT systems at the location of where now a battery is placed. So, of course, we need to be able to shrink down the system to a much greater degree than we need to do in the external system. But what it allows us is to serve a lot of applications that could not work with an external power box. And here we predominantly see a market for trackers, for example, Bluetooth beacons and all kinds of wireless asset trackers. Then the final step and the third step in this roadmap that we have is an even smaller version where we really go down to MEMS scale and be able to integrate this on a PCB in a microelectronics package, and to have like a proper MEMS device that you could use in, for example, consumer electronics or maybe even medical applications.
Okay, I think it sounds like a very thoroughly planned roadmap. It's good to see. Actually, this was like going to be my future question, that where do you see the scaling factor coming in, and basically how small do you think we can make this? So you've already answered it, that it will be integratable on a PCB, which already sounds very exciting. So Thijs, do you see any manufacturing challenge coming up in making these MEMS based sensors in future, or maybe in any near future, maybe next year? Or are you currently facing any manufacturing challenge that your team is able to solve?
Yeah, so it's the structures that we make, these compliant mechanisms, they are mechanical structures, and we introduce something called buckling in there, which typically is something that you want to avoid as a structural, civil, or mechanical engineer, because buckling, it really collapses the structure. And if this happens in, for example, a bridge or a column that has to carry load, then it can really be detrimental for the structure. We do that in a controlled way. And that is what gives these mechanisms their unique properties of being able to harvest energy from this wide range of frequencies. Now, getting a compliant mechanism to buckle on a large scale is quite doable because you can still handle it. And what that means is you take the two ends and you compress them more together. On the micro scale, particularly at MEMS level, not only do you have to be way more careful at how much of this compression you apply, because suddenly all of the materials are super brittle. For reference, we now use spring steel for some of the structural elements. And at MEMS scale, this has to be silicon, which is a way more brittle material. And on the other challenge is that it's extremely hard to do this at such a small scale because you cannot manually handle the mechanisms anymore. So you need to come up with a way to reliably introduce this mechanical stress, this preload we call it, in that mechanism without having to go through some manual handling step for that. So you need to think about maybe some smart assembly features or maybe some smart process steps that allow you to get that stress level embedded in the mechanical structure.
Okay, and I hope you are on the track to solve all these manufacturing challenges. As you know, I think your roadmap requires, if in future we want to see these sensors on PCB level. Yes, so is there anything your team is doing to solve or to work towards solving these challenges?
Yes, yeah, absolutely. So currently we are still at that larger scale where we develop our prototypes, but we are quite fanatically building models of the mechanics and of course the resulting dynamic behavior in a way that we can also use that to design these systems at micro scale. So that is one track of all the modeling and simulations. And the other track is that we are investigating the manufacturing strategies and the production recipes that we could use. So we try to get like an overview of the technology landscape there in order to make these systems at that micro scale level. What that means, what processing steps could be used, for example, to get this buckling effect as part of the manufacturing routine already in the mechanism, or what other strategies could we use? For example, having a structure around the mechanism that you deform in a particular way, which is easy to handle with larger scale tools. And those kinds of really fundamental research topics is something we are addressing quite actively now in preparation to making that step towards MEMS scale prototypes.
Okay. I feel like, your team's technical expertise and your own technical expertise and educational background on this, it gives you a very good leverage on, that you're able to identify and solve these challenges. So, Taich, in future, and this is like coming purely from my curiosity of, somebody from outside domain. So is it possible that in future we might see similar MEMS type of sensors maybe embedded in, let's say, clothes of athletes on such smaller scale, like in maybe electric cars, so that they can utilize engine vibration to charge the batteries, or on road vibration or tire vibration to charge the battery? Do you see is there anything like that you have envisioned as a founder of this, of Memsys?
Yeah, I think the clothes example, it is one that is also described in literature quite often. And there are already a lot of developments being done in shoes, for example, in running shoes, where quite similar techniques, also based on piezoelectric materials, are used to feed power through integrated sensors in, for example, that shoe, to figure out how you are running, and if there are maybe some, like the shoe is wearing out, or there are maybe some issues in your running pattern to address. Those applications, smart clothing and shoes, for example, definitely I think we're going to see more of that in the future. It's maybe not necessarily vibration based, more like force based energy harvesting, so a deformation of the shoe itself. That's how you generate the power. In terms of electric cars, the power levels are so different here, right? So we are talking just yet about milliwatts. And of course, the battery of your electric vehicle, it holds easily kilowatt hours. So it would take many decades to charge a electric vehicle battery. So I don't think, as a primary source of your fuel, essentially, I don't see that ever happen. But what I do see happen is that there are many sensors in your car that are currently either wired up or powered by batteries. And tire pressure monitoring sensors are one of the key examples, I think, also provided in a lot of literature on energy harvesting. Now, those are, of course, excellent candidates for applying a vibration energy harvester as a power source. And that means that if your car is moving, it is generating vibrations, and therefore charging or generating a little bit of energy locally, which means you could power that tire pressure sensor in your wheel with the energy that you generate locally, instead of having to bring that energy there through either a cable or a battery.
Makes sense. So, again, and this is like among last few questions. So, who is an ideal customer for you in this case? Like, who can benefit most from Memsys technology?
Yeah, so what we currently do in our commercial strategy, we try to work with the users of sensors. So that is for us right now on that external product, that is companies specializing in predictive maintenance. For example, placing sensors at asset owners, at factories, and then watching the values of those sensors such that they can advise on when to do maintenance and for how long that equipment still has relevant life. That are the users of the sensors, but we also need the producers of the sensors. And that are typically electronics manufacturers, sensor builders, and we need both of them to succeed. We need, our ideal customers are currently both of these groups. So the sensor producers are our direct customers, but the sensor users have to give them, of course, the incentive, because they are the main benefactors of our technology. And we need both.
I think, yes, I think sensor users will push sensor makers to, that I want a sensor that is locally powered rather than in which I have to implement a battery. I
Yeah,
think
frankly, I think sensor users don't care, and they shouldn't care so much how the sensor is being powered. But what they will care about is that they have to make sacrifices on the performance of that sensor if they want to achieve this 3, 4, 5, 6 year lifetime. And what that means is maybe they can measure only one time per day or one time per hour instead of continuously. I think that is the main drive for the sensor users, that they can get more value out of the sensors, out of the existing same sensor installations, and they have to spend less resources on replacing those sensors, and particularly the batteries in those sensors once they run out. So that's in conjunction with maybe reducing the ecological footprint or some safety concerns that are going hand in hand with battery replacement, or maybe some shutdowns that you have to do in order to even access those machines where the sensors are placed on. That is, I think, the main driver for sensor users to adopt these kinds of technologies instead of either batteries or wires.
Right. I think so. It not only makes their life easy in terms of maintenance and taking care of these sensors, it also opens up an opportunity for like better analysis and a better data collection, because you don't need to worry about keeping using your sensor maybe once a day or frequency that you can run. If there's a continuous power, then you can you do continuous monitoring. So I believe that's a great USP to work with you. So I think, Thijs, so that was, I think I'm at the end of my questions line. There's just one more thing I'd like to know from you, and that is it is related to your background, and your, since this is your first venture, and you have done PhD in relevant fields, and you right away started a venture in such a niche area, and it is very niche, right? Very less companies are active here, and this is not a problem that is being highlighted a lot out there, but it's a huge problem, as we discussed, 80 million batteries, 40 million sensors. I'm sure you might feel like, because all the founders and venture seat initial entrepreneurs, they feel this way, that maybe this is not going to work, or maybe this is too difficult to scale, or maybe it will fail. So I'm sure you might be facing such feelings as well. So my question is, like, how do you overcome those, or basically what keeps you going in these situations, working in such a niche industry and solving such a niche technical problem, and still pulling through?
Yeah, it's I totally recognize that. Those feelings, I think it's a emotional roller coaster, right? Founding a startup, but also being closely involved with a startup. I don't think those feelings are unique for founders, but I for sure do share my part in that as well. What I like to go back to once am really down and think, yeah, could this work? Could this even be brought to market? Can we make them cheap enough? Can we convince customers quickly enough of the value of what we are building? Is I think that it really helps with having the technical background and having worked on this research now for over 6 years during my graduation project and PhD, that there is a very clear understanding of the fundamentals. And to me, if I flip the picture around, right, we would be using energy harvesters right now everywhere. And I would propose to have this solution with batteries that run out after a certain fixed amount of energy, that it just totally doesn't make sense to me. Why would it would be so natural that we are generating the power locally at those sensors? And that picture in my head, it really gives a comfort that this is, from first principles, a very logical way, or a very logical solution for powering IoT devices. And yeah, that gives a lot of, let's say, mental support, even in especially in those difficult times. It gives a lot of support knowing that the first principles are right and that it makes sense, that you're not totally crazy for thinking that this application, that this technology in such an application could have value. I think that is, yeah, along of course with all the people I gathered around me in these years. So we have a fantastic team. I have two co-founders. We have a bunch of investors that are really actively involved, and their enthusiasm and their ambition and their let's say how this thought, this idea lives on in their minds as well and develops further than what I could do on my own. That also gives a lot of hope and a lot of comfort, that it is not like during the PhD and the early stages, especially of it, you are quite alone in believing that this has value and that you're working on it on your own. Now we are working on it with a team of very intelligent, with a lot of technical expertise, critical people as well, and they are believing in this as well. And that is really helping me and my own beliefs to strengthen that even more than I already had purely on my own.
I'm with you on this 100%. I also, it doesn't make sense to me as well, because when I initially started my career here at Gravy and I started working on technical documentation, so I was writing about one article about future of IoT. So it was like an initial assignment for me as a marketer. And at that time I thought, these sensors, in home it makes sense, you might have like 20-30 different sensors, like temperature sensor, humidity sensor, those kind. But on factory level there are like, there could be millions of sensors as well, right? Imagine Amazon's shipping warehouse, so there could be like millions. So it doesn't make sense, like how will you even track which sensors require battery replacement, which, where does this wire go? So you are absolutely right, and I'm with you 100%. It doesn't make sense to power them through batteries or wires. They should be powered locally, and I'm glad we have lots of companies working on the solution, including Memsys.
Yeah, thank you.
Sorry.
Yeah, and it's a fantastic space to be working on because it is quite niche, as you said. It is also involved with a lot of hardcore mechanical and electrical engineering challenges.
Hmm.
There is a certain depth to it that it's not an obvious problem for if you're not familiar with this industry and the problems of wide scale deployments of IoT. It's not such an obvious problem as that maybe many other startups are working on. But it has been recognized, at least in academic research, for quite a while. And I'm very sure that it is a real problem and it is worth solving. And we will never know ahead of time if it's a problem that will be solved in the next 5 years, in the next 10 years, or maybe even longer. But I do know that we are now in a position to give it a shot, and that is what we are going to do. And so far, yeah, we are having, let's say, we're continuously learning and solving, like better equipped at solving this problem than we were yesterday. And as long as I have faith in that we are doing that quick enough, and yeah, I can convince also people around me that we are, I do for sure see a very bright future for Memsys, but also for energy harvesting technology in general.
And with that, I think that was it. Taish, thank you for giving me such a thorough breakdown of your technology and the journey that Memsys is going through. I really appreciate our conversation. I learned a lot about it. So thanks for giving me your time.
Yeah, Shabas, thank you very much as well for the questions. I think you genuinely did a very good job with not having sort of the basic questions that everybody wants to ask. But I really liked answering them. I think big thank you for that as well. It was a very interesting discussion, and I really like to yeah, to answer your questions and to also get your. It clearly shows you have been putting in the time to investigate this, and you are quite knowledgeable on IoT and the challenges involved with that. And it was a great conversation. Thank you very much.